Yep.
All right, class, I was asked to work some problems. I want to do two things before I actually work these problems. Then what I'm about to do may answer some questions. I'm not sure. And who asked this? Somebody asked. It was, no, not him. Somebody asked me about this in class, and I didn't actually. I wanted to show you both ways of doing this, but let me go ahead and do this. They asked me, how do you do the inverse transform of s over s plus like 2 squared? They want to know how to get back if this is x of s. And I said one method is this. I said I know if I have 1 over s plus 2 squared, I'm assuming you know this by now, that's really t times e to the minus 2t u of t. Do we all agree on that? If it was just 1 over s plus 2, it would be e to the minus at u of t, right? And then if it was a square there, that means it's going to take it and multiply by t. Correct, class? I mean, I'm just putting that out there. We talked about this sometime. Now, if it's got an s there, here's the way you probably should do this one. Go ahead and say that's a double pole, right? Just take s over s plus 2 squared. Say it's equal to some a over s plus 2 plus b over s plus 2 squared. Now you know how to go back to the time domain, the inverse of both of those, right? Those forms, they're easy. So if I take a look at this to solve for b, I can see the pole is at s equals minus 2, and that's the highest order, of the actual complex poles, really. This is second order pole. So I multiply through by s plus 2 squared, and I evaluate this side at s equals minus 2. Do you all agree with me there, class? Give me a show of hands if you do. How to get that? So this is minus 2. Now, this is up to you. A lot of you just get a common denominator, right? Solve for a. If you've got that far, class, and that's acceptable. If you want to do that, you can say this is really going to be equal to s plus 2 squared, and I multiply a here times s plus 2. That's where we have an s plus 2 squared over here. And then minus 2 has to be equal to that. And I look at the coefficient of s, right? I have as here, a times 2, a times minus 2, and I can say the coefficient of s is a, the coefficient of s over there is 1. Do you all see that, class? I'm going to see this right here. You all see it? It's straightforward, it's not hard. So this is 1. Now, therefore, if I want to go back to the time domain and get, if this is x of s here, and get my x of t, now I can see this one goes back as what, class? Yeah, e to the minus 2t u of t. And this one goes back as 2 first, right? Minus 2, put the coefficient there, don't forget that. All right, right, class? Minus 2 times what? T times e to the minus 2t u of t. The other way I was suggesting, and I guess I didn't make myself clear, I could say if I knew that this goes to that, right? Then I know if this is like my, quote, I'll call it my x1 of t. If I take a derivative of x1 of t with respect to t, what I get is s times x of s minus x of t equals 0. Correct, class? How many of you know that? You have to know that one, right? With me? Well, if this is my x of t, what is x of 0? Just plug in 0 for t. Class? 0, correct, class? 0 times anything is 0. So this goes away. So you could just as well say if this is x of t, I could take a derivative of that, and I would have the actual time domain version of s times x of s, where my x of s was this. How many see this right here? Understand? That's both of those ways are legitimate. Do you all see what I'm pointing at right here? Either way gets you the right answer. Either way is correct. If you prefer time domain derivatives, do it that way. If you prefer just an expansion, do it that way. All right, I hope I answered your question, because you asked me that, I think, didn't you?
Something similar.
I think that was it. I had it written. I didn't watch the video, but I had it written.
I had a question on the transfer function, a to s, just on the decomposition.
Okay.
It's 2s squared minus 4s minus 1.
Is this on the numerator?
Oh, the numerator, yes. 2s squared minus 4s minus 1. And the denominator is s squared plus 4s plus 3. And you had, like when you wrote it down, you had a plus c. It was just not over anything, and I was wondering how you came up with that.
I divided this into that.
Oh,
So if you divide that into that, the first term you get is 2, don't you?
yes.
And then plus the remainder, which is going to be the minus 4s minus 1 over that. I mean, I can do it for you if you want me to, but remember, these are the same order, right? That's s squared. So that means you have to divide the denominator into the numerator, and you're going to get a constant. That constant will be 2. Do you all see this, class? Then the remainder you can do an expansion on. Are you with me?
Yeah, I believe so.
That's what I think I did on the board, didn't I?
Yeah.
I did that? How many understand that? All right, remember, same order, divide bottom into top. In the remainder, put over the denominator and do expansion on that. Important, very important.
Okay.
All right? You know, I do want to tell you that Wolfram Alpha and MATLAB both can do both the inverse transform and the transform, Laplace transform of anything. They'll get you many forms on Wolfram Alpha. You might see 5 or 6 different answers, all that are basically the same thing in different forms. Yes?
Symbolab is a better option as it will give you steps along the way.
What is this?
Symbolab.
S-I-M?
S-Y-M-B-O-L-A-B.
Oh, symbol. S-Y-M what?
Symbolab.
How many know about that? Oh, fantastic. Outstanding. Send me that link, all right?
Okay.
Because I'll put it up. Anything, I'll try anything to help you guys. All right. Now, I'm going to get to you, whoever put me that question you want me to do. I want to do just 2 things here, all right? And I think this might answer some of your questions. Now, last time when we talked about doing like circuits problems or differential equations in the Laplace domain, what I suggested was replacing inductors by simply SL and capacitors by 1 over SC, right? That assumes no initial energy stored. But a lot of times, especially with transient problems, when you had Dave Irwin's class, there was always initial conditions. A voltage on a capacitor, a current in an inductor, correct, class? So you had to include them. So now I'm going to show you how to go about taking care of that. And so you're going to include the initial conditions. If you have just an inductor, for a resistor it doesn't matter, just an inductor here. And this inductor has L, and it has a current I of T coming into it. And it develops a voltage here, V of T. Well, I know for that particular problem, if you can't see L, you're way in the back, you really see this. Outstanding. All right, then I know I'm going to have I of T is equal to L times di of T dt. Do you all agree with me? Right? That's fundamental for an inductor. You have to know that one, right? You're an electrical engineer. It's what? L di. You should have yelled like crazy. You can throw tomatoes at a mistake like that. All right, following voltage is equal to L di dt for an inductor. Now take the Laplace transform of it. So when you take the Laplace transform, I get V of S, that's the Laplace transform of this, is equal to L times the quantity. The I dt would be S times I of S minus I of 0. This term is the time domain value of the current at time equals 0, just as the switch is, just as the event starts. Are you with me, class? How many see this right here? Now we rearrange this. And really, it doesn't need a lot. Actually, we don't even need to rearrange it. I can say this is just S times L times I of S. And it's going to be minus L times I of 0 is V of S. Now, I prefer to do this in terms of a series circuit. So I can say that the actual voltage on this inductor looks like something, if this is the voltage right here to minus, it looks like if I have a current I of S here, there would be an impedance SL here, because SL times I of S would be that portion of V of S. And then there would be a voltage source here. You'll notice the voltage source, the voltage here, if I have I of S times that, it would be plus to minus. But this will have a minus to plus sense. And that will be equal to L, and it's a voltage source, times simply I of 0 plus. And this, right here, is the equivalent you would substitute in for that inductor. Now, what it means is you would have an impedance of SL, and then you would add to that this L times the initial current. Understand, class? How many see this right here? We're going to do some problems, but I've got to make sure you see it. And I haven't forgotten you, don't worry, I'm going to get to your problems too. Now that simplifies a lot of stuff, because now I don't have to write differential equations and then do Laplace transforms of them. The next is when we have a capacitor. So if we have a capacitor right here, and we say this is the voltage on the capacitor, and there's a current I of t into the capacitor, right? Well, if we take a look at this, I know that the differential equation that describes this is C times dV dt is equal to I, right? And this is I of t, V of t for the capacitor. Do you all agree with that, class? C dV, it takes a time rate of change of some voltage on a capacitor in order to get an actual current. No change in voltage, no current. And with an inductor, it's just the opposite. If you have no change of voltage, you get an infinite current. An inductor is just basically a bundle of wire. So if it's at DC, it's got basically no resistance and the current just spikes to infinity. But if there's a time rate of change of something, then there is an impedance that slows it down. So for this one right here, now this becomes I of S, right? If we go into take the Laplace transform, C times, and this would be S V of S, right? And then it's going to be minus V0. Y'all agree with that so far, what I've done? I'm going to rearrange the terms. I want to get in terms of V, not I. So if I take a look at this, first thing I'm going to do is divide by C, and I get rid of that term. And now I take V0 minus to the other side, so it's plus V0 here. I'm just modifying this so I can get Vs by itself. Are you with me, everyone? And now I divide by S. So now I can say that the V of S that would occur here, right there, I could replace that capacitor if there was a current I of S flowing in. I could put a capacitance here, replace the capacitance with 1 over SC times I of S would be the voltage across it. That would be this term. Then I'm going to put another thing in here, but this time the polarity is additive. And it's going to be plus V of 0 plus over S. And that's the way I could replace the capacitor with an initial voltage. And then I would solve the circuit's problem just the way you've been doing it. Mesh, right? Or nodal. Or just by doing what? Using combinations where you take things in parallel, find one value for that. Things in series, add them together, find one value. Are you with me? Now I'm going to do a couple of problems to show you this. And I will get at your problems in a second. But how many understand this? It's going to take a few minutes to remember to put this in this way and to put this in this way. But when you work about 5 problems with each of these, and then you've got it. Then you can never get it. You can always write differential equations. I'm going to do that with the next problem to show you what I mean. This is going to be the brute force awkwardness method. That's the first thing you do when you do Laplace transforms, is basically write a differential equation for the physical event you see until you get used to it and know how to do substitutions like I'm showing you here. So, and most of you know this, differential equations, or for discrete events, difference equations, they describe everything in the universe. Everything that we see and hear are basically describable in terms of integral differential equations, or just differential equations. And we solve those by finding the boundary conditions. And then we can get general solutions. It doesn't matter if it's in 3 dimensions of space and 1 in time, or if we go to something where you have n dimensions, and those are for theoretical physicists and people like that. But it really doesn't matter. Differential equations are the key. And for physical phenomena, all the differential equations we use to describe them are based on measurements. Maxwell's equations came from observations. Sir Isaac Newton found the acceleration of gravity here on Earth by measuring it. All the things, the differential equations, are based on observation. That's what I'm saying. Pure mathematics is not necessarily that way. You can come up with abstract laws that aren't applied in a physical universe, but the things that we deal with are applied in our universe. Understand? So the differential equations are always based on, well, should be based on the physical laws that govern behavior. Now with circuits theory, it's actually quite easy to do this stuff. So I'm going to show you a general circuit. This is the first, most obvious one. If I have R here, and I have a capacitor C, now this is the one you're used to seeing, and I'm going to show you why what we do is so important. And now I'm going to have a voltage here, and I'm going to let this voltage be equal to plus to minus, say 4e to the minus t right here. Instead of just, I'm going to make it 4e to the minus t, generally so, but I'm going to have a switch right here that closes at t equals 0. Now you're used to seeing this being just what? A constant value, right? 10 volts or something for your circuits problems, right? How many remember those? That was a standard RC problem. All right, well with this one I on purpose did it this way. Now this switch closing at t equals 0 means everything over here is disconnected until the switch is closed. I'll put this as a capacitor C, and I'm going to say this is my output voltage. I'm going to call that just y of t, and that's what I'm after. I want to solve for that. For t greater than 0. For t less than 0, it's 0. Do you all agree with that?
Yes.
Now, keep going with me. So when the switch closes, really, instead of closing that switch and having a mechanical thing, I can just short that, right, and put a u of t here. And now everything starts at t greater than 0. I did not put an initial condition on this one for a reason. With me, class? So now, first we write the differential equations. And you know with these type of things, here current I of t is the thing that's constant for both of them because it's a series circuit. Do you all agree with that? Show of hands here, right? Remember these in physics? Didn't they teach you to write the differential equation? I don't really know. Well, they should have. So when I come here and I write the differential equations, first thing I notice is here that my I of t, you agree that I is the same through all the elements, class? Do you all agree with that? See? So I can say I of t here through that capacitor is equal to C dV dt, but it's also equal to C times dy dt, because y is the thing I'm looking for, the output voltage. How many see that right there? Agree? You see it right there? I want to make sure. If you're not seeing something, don't be embarrassed, just yell. There's no dumb question except the one that's not asked here. So now, I equate the voltages. I say the sum of all voltage increases, which is this, is equal to all the voltage decreases, right? So here I get the 4 e to the minus t u of t equal to the voltage drop here. What's the voltage drop there, class? Just R times I, right? And what is I? I is C dy dt. So it's R C dy dt. Right there. Plus y of t, right? Equals 4e to the minus t u of t. Now the thing you're not used to is writing equations where instead of just writing current, you write current in terms of a voltage differential. Follow me, class? This is the difference. You could solve for just current. And then if you solve for just the current, you could say that the voltage here would be C times the derivative, it would be the integral of the current with 1 over C in front of it from 0 to t. You could do it that way, but it's better just to go right at that value, y of t. Because that is the thing we're looking for. Do you agree with this? So go ahead and solve this. Well, if we take the Laplace, first I'm going to divide everything by RC because I want the coefficient here to be 1 of the highest order derivative. So if I divide by RC, I get this. With me? Now I take a Laplace transform of both sides. Here I didn't put an initial condition for a reason. We're going to get the simplest one. So if I just take a Laplace transform of both sides, here I get 4 over RC, right? And then it's going to be times what? Just 1 over S plus 1, isn't it? e to the minus t, u of t, is just 1 over s plus 1. How many see that? Other side here, I said there was no initial conditions. I of 0 plus is equal to 0. So this is just s times y plus 1 over rc times y of s. So it's going to be, I can write this as y of s times 1 plus 1 over, I'm sorry, s, pardon me, times 1 over rc. Do you all agree with that much? I haven't given a value to rc yet. You all see that, class? I factored out the y of s.
Wait, explain to the right side again.
All right, when I take the Laplace transform of that, that is s y of s minus y of 0. I said where y of 0 is going to be 0. There's no, I'm sorry, I should say the voltage y of t is 0. Is 0, my bad. I'm trying no initial energy. All right, and then this is just what? Y of s over rc, right? So if you factor out the y of s, you get s plus 1 over rc. How many see this? I'm not trying to make this complicated. I don't want to spend too much time on it. Do y'all agree with this? All right, now, if I'm solving for y of s, I divide this side by s plus 1 over rc. And now I have y of s. Does everybody see how these are two simple poles? I have a constant 4 over rc. I have the first pole, s plus 1 over rc, right? And I have a second pole, s plus 1. Now the value of rc determines if this is a double pole or not. If rc, 1 over rc was 1, then I'd have 1 over s plus 1 squared, right? And when that went back to the time domain, that would be a t e to the minus t u of t. If they're different, then you will have two distinctly different exponentials decaying, different constants. How many see that? But that's the general form. How many see that down there? Now that's brute force and awkwardness in terms of I had to write the differential equations and I had to solve them, and I didn't even use initial conditions. Now I'm going to say one thing. If I had initial conditions for this same problem, and I'm going to give 1 over rc a value to make it a little more real. Let's call that 2. Why? Because I feel like it. No other reason. So this becomes 2, right? Then the coefficient here is 2, right? This y of s would be the solution to that one. Agreed? Now I go back and I say, that would be the solution when that's 2. And that's not a hard one to do to get the inverse of. Now I come back up here and I'm going to do something different. Now I'm going to say y of t equals 0 is equal to 2. All right? So the initial value on the capacitor voltage is 2 volts at t equals 0. Follow me? The differential equation still remains the same. This is the brute force approach. Now I go ahead and I'm going to say, when I get it down to here, and this is 2, by the way, RC is 2, so the coefficient of this is just 2, isn't it? Correct? What? I'm sorry. 8, you're right. 1 over that 8. My bad. Thank you. Agreed, class? Now I'm here, and now I'm going to go ahead and put in the initial condition of 2 and solve this. So please watch this. This is the difference. And then I'm going to do it just by substituting in what I had before for how you put that value of voltage in. Okay, class? Just watch this. So for this one, now this becomes what? S times y of s minus y of 0, which is 2, right? Plus, then it's going to be 2 times y of s. Do you all agree with that on that side? How many do right here? On this side, this becomes simply 8, right? Over s plus 1. Everybody agree with me? I don't want to go too fast. Do you all see what I'm doing here? I've added the initial condition with the fundamental differential equation. So I'm showing you, we're going to the next level, and then I'm going to show you how much easier it is just substituting in that capacitor is 1 over SC plus the initial voltage. All right? Now what happens here? Well, I take the minus 2 to this side, becomes plus 2. Agree? Right? And then I factor out the S plus 2, don't I? Out of the y of s. So on this side, Here I get y of s times s plus 2. And then I divide both sides by s plus 2. And I have this. Remember, I added an initial condition. Do you all agree? Now you can see that this one goes back to the time domain very easily. That's simply what? 2 times e to the minus 2t u of t. Do you agree with me there? How many realize you can get this pretty easy by taking a over s plus 2 plus b over s plus 1? Right? You all see that? And I bet you every one of you can easily get the time domain solution for that one, right? All right, these are all simple poles. Now, another way to do this, and this is why what I showed you just now is so valuable. Instead of writing differential equations, and remember, this is an extremely simple circuit. This is one loop, right? You have 2 or 3 loops, oftentimes, 2 at least, with inductors and capacitors, and writing diffie-qs for those gets, at best, painful after a while. It gets really tedious. But if you just replace the elements with the initial conditions and the impedance, it becomes easy. Now let me show you this one. What did I say the capacitor could be replaced with? Remember? I had here, I said if I had I of t, this is C, this is C right here, then I had dv, or I said I of t is equal to C times dv dt, right? Or I said what? I of s was equal to C times the quantity S, V of S, right? Minus V0. Correct, class? I'm just trying to show you. I'm going to get Vs by itself. I'm doing it one more time here. You all agree with that, first of all? Now, I'll divide by C first. Then I'll take V0 to this side. Takes that out. And then I divide by S. And now I have, you've got it on your paper. I'm working it one more time. So I have SV of S. Now I can say that if this current I of S, and this is my capacitor here, the voltage here to here, this is C, this can be replaced as simply an impedance of 1 over SC, and then the voltage will be additive, will be plus to minus V of 0 over S. Do you follow me on this, class? And this would be, it's I of S, by the way. This is what you replace the capacitor with. And remember, when you have multiple loops, you just do that. But you have to get the current through the capacitor. So you have mesh currents, you have to say the current, the net current that I'm showing there is the current going into the head of the capacitor minus the current leaving it. Follow me? So with mesh, you always have those currents, I1, I2, that are doing this thing, all right? So be careful about that. That's the reason nodal is much easier. So if I take a look at this right here, in this circuit, with the initial condition, I had RC over 1 equal 2, and I had Y at t equals 0 plus equal to 2. So now I come here, I'm not trying to go too fast, but now what I can say is this. I go ahead and I take the Laplace transform of any time domain function right off the bat. We're going to do it right here in this circuit, and this becomes simply 4 over S. Do you agree with me, class? This is 4 over S. Put it in there. Now this is, 4 over S plus 1. Pardon me. 4 over S plus 1. I'm sorry. Follow me? I'm just showing you. Now this is an electrical source. That's the value of the electrical source. 4 over S plus 1. Here, that's the resistance. I said 1 over RC is 2, so I'm going to make R1. How's that? Can't get any easier than that. And I'll make C a half. All right? So C equals 1/2. Yeah, I'll just put C equals 1/2. Make it easy on myself. Now when I do that, this is just going to be R. In the Laplace domain, a constant, the R's stay the same. No variation. Here, now this is going to be replaced by the equivalent, which is going to be 1 over SC, or now I'm going to say the impedance of this. Here's what I'll do. This is going to be 1 over S. C was a half, so it's 2 over S, right? Class? plus, and then you'll notice I have to put down there the initial voltage right there divided by S, right? The initial voltage was 2, wasn't it, class? So now I go ahead and put it right here. I put a voltage source here, plus to minus 2 over S. Right? Some of you noticed something. What can I do with those two? Make it 4 over S. How many see that? Agree with me? Yeah, sure. So I can take these and just say, why not just make this one singular thing and make this 4 over S? Because they're both additive. Now, you see what I've done there? 2 over S plus 2 over S is 4 over S. Agreed? Now what happens? When I'm doing this right here, remember this is an impedance, right? Now what happens here when you do this? Well, how many see what's going on here? If I want this voltage right here, I can get it a lot of ways. How about if I take the source voltage, 4 over S plus 1, that is the source voltage, right? Isn't this like voltage division? So then if I take 4 over S over 4 over S plus 1, wouldn't that be that voltage right here that I'm looking for? I should say this would be my V or Y of S. Sorry, Y of S. Do you agree with me there? Yes, sir.
Quick question. How are you able to add the 2 over S and the 2 over S?
Aren't they in series?
Yes, but isn't one a voltage source? And
It
one
is,
a
it is.
Impedance?
They're in different units.
Well, wait a second now. I did this. If this was 2 over S here, let me do it this way so we get it right. And this was plus, actually, you know, you're right about that. I think it'll work, but you're right. Let me do it. Let me just do it this way, and I won't lead you astray. This is a voltage of 2 over S. This is impedance. You're absolutely right. All right, now with this, I'm going to do it this way. You're right. You're right about that. This is a voltage source. If I'm going to do this, since this is an impedance, it has to be multiplied by the current, but this is going to be the same. And now I can just take the sum of the voltages around any closed loop and set them equal to 0, and I'll do it that way. So I get an increase of 4 over S, right, plus 1 here is going to be equal to simply, we're going to get I of S then. I didn't want to do it this way. This is I of S. Then it's going to be I of S times 1 plus I of S right here times 2 over S. And then it's going to be minus 2 over S right there. And that's 4 over S plus 1. I've just,
Should not equal S2 and S then.
well, from here to here, isn't it a decrease? Oh, wait a second. I'm sorry,
Yeah,
it
they're all
is, you're right.
decreases.
I'm trying to get through this thing too quick. You're right about that. I'll slow down. Do y'all agree with me there? I apologize for this. Catch me if I make any more mistakes. Now I'm going to take the 2 over S to this side. You'll get the same thing. It's minus 2 over S, right? Now typically whenever I see a 1 over S term appear, I multiply both sides by S instinctively because I don't want a 1 over S anywhere. I know I'm going to be doing so. This gets rid of this S, and this puts an S here, and that gets rid of that S, and it puts an S here, doesn't it, class? And then I get I of S times the quantity S plus 2 over here is equal to 4S over S plus 1 minus 2. And finally, I divide by S plus 2. And I have my I of S. Now once I have this, these are simple poles. You can take it back to the time domain. Can you not, class? I want to try to get at your problems before we do the quiz, whoever asked that. I know you're on it somewhere. Oh yeah, you. Which was the first one?
No, if you could work this other problem, then it would be sufficient.
Which one?
This one right here, number 1.
Just tell me. Just tell me.
That's a lot of stuff.
I mean, is it a circuits problem?
Yes, sir, it is.
It's a lot of stuff. All right.
Yeah, I stuttered when I hollered.
It's all right, it's all right. This one? All right, that's 20 e to the minus 3t. This is what I just did, really. I mean, it's the same basic thing. 20 e to the minus 3t. Go ahead, what's the resistance?
10. Yes, sir, 10. The inductor's 50 millihenry.
Is this inductor here?
Yes, sir.
Inductor L equals 50 millihenry.
Yes, sir.
They want the voltage in?
1 voltage across there. Yes, sir.
All right, guys. We're going to do this. Call that V out as T. What is there an initial condition or not?
No.
All right, there's no initial conditions. This one's easy. We'll go right to the complex, to the S domain. Work with me here. Please make sure you see this. Now there's a U of T here, isn't there? Class, is that 20 U of T? 20 e to the minus 3t U of T? We're going to do this slowly. This, when it goes to the Laplace domain, becomes 20 over S plus 3. Do you all agree? It's still a voltage source, though. And I'm going to go ahead and put a V on here just so I don't mess up it. So this is going to be a voltage source. Now, that's still 10 ohms, period, right? This here now is going to be S times L, correct, class? S times L, or the impedance here is 50 times 10 to the minus third S is the impedance. Do you agree? That's in ohms. This is in ohms, this is in ohms. Therefore, this voltage V of S, V out of S, now I'm going to do it this way. I'm just going to take this impedance over this impedance plus this impedance times that voltage. I'm using simple voltage division. See it? Everyone? So I can say that that is equal to 20 over S plus 3. And then it's going to be times 50 times 10 to the minus third S over 50 times 10 to the minus third S plus 10. At this point, you can see it becomes easy, fairly easy. Divide top and bottom. I'm going to divide top and bottom by 50 times 10 to the minus third. Understand? So I can get a 1 there as the coefficient of S. Everybody see that? I need 1 as the coefficient of S. So that goes away. That's 5 times 10 to the minus 2. 5 over 100, 1 over 20, so 20. This becomes 200, I believe, doesn't it, class?
Yes.
So now I have this. You asked this, I hope this is answering everything. Now I can say, we can expand this, right, and say that this is equal to some A over S plus 3 plus B over S plus 200. Do you all agree with me, class? How many do? Now, you're going to have to help me with this. Let's see, if I multiply by S plus 3, right, and I then go ahead and put in a minus 3 for S here, I get what? 197 into minus 3 up top, right? Times 20. Do you agree with that? Can you just give me the number? I don't.
So minus 60
It's
or
negative.
What is it?
minus 60 over 197.
It's negative 0.05 or something like that.
Minus 0.3. Say it again.
0.5.
0.5. And what's B?
20 plus.
What?
20.35.
20.35. Now, when you do that, how many see they go right back to the time domain as simple exponentials? Everybody see this right here, class? You guys see it? Who asked that? You asked. No, he asked. Do you see what I'm doing here? Yeah.
How did you get the S plus 200? What's it?
I did this. Do you agree this is an impedance right there? So what I did is voltage division. I took the source voltage here, and I multiplied by the impedance of this volt, where I want the voltage, divided by the impedance of this plus this. It's like two resistors in series.
So how did you get 200? Would it be?
Now I divided, this is going to be what? 50 times 10 to the minus third, right? Divide by that. What is that? It's 5 times 10 to the minus 2, right? Or 1 over 20, isn't it? So 1 over 20 I divide by, or multiply by 20, I get 1 there, and 20 times 10 is 200. Follow me? It was just division. It was in all. How many see this right here? All right, guys, quiz time. Do me a favor, spread out one desk between you and your neighbor. Monday is a very important class, by the way. So make sure you're here Monday. All right. Try to get one desk between you and your